Okay, so uh, let us study some example. For example, let us have some equation of this kind. We can dx squared plus plus 3 dx dy plus dy squared plus let us add some constant term plus dy plus 1 acting on u equals to 0. So the problem is to solve this equation either to write general solution or to write some solution with some boundary conditions. So to solve this, we need the change of variables from this equation to some canonical form. The first thing to do is to do something with this quadratic form. What did I write? Equals to 0. We can collect here the complete square, like dx plus 3 over 2 dy squared minus 9 over 4 dy squared. It is these two terms. And here we had dy squared plus dy plus 1 acting on u equals to 0. Let us call this variable new, let us call this operator new dx, some dx prime. So let us define dx prime equals to dx plus 3 over 2 dy. And here we will get what? It will be minus 5 over 4 dy squared. So let us define the following, that dy prime equals to square root of 5 over 2 dy. So in terms of these operators, it will look like dx prime squared minus dy prime squared plus, so this dy should be expressed in terms of this dy prime. So it will be 2 over square root of 5 dy prime plus 1 acting on u equals to 0. Now it's not a canonical form of this equation because there is this term. So let us do another transformation. It will be 1 over square root of 5 plus 1 minus plus 1/5. Okay, we have this, and now how to achieve this this transformation. We noted that dy prime minus 1 over square root of 5 equals to e to y prime over square root of 5 dy prime e to minus y prime over square root of 5. If we now denote this times u tilde over u. So, oh, or let us write it once again. So this equation is written as e to y prime over square root of 5 dx square prime squared minus dy prime squared plus 6 over 5 e to minus y prime over square root of 5 u equals to 0. So let us denote this new variable u tilde. So this u tilde satisfies this Klein-Gordon equation with some non-trivial coefficient here, but it can be scaled by scaling x prime and y prime. It is not very important, but still doable. So, and when we have this, we can already recover the correct variables. Actually, well, maybe we can also rescale this coefficient, saying that let us multiply it by 5 over 6, and say that dx prime equals to square root of 6 over 5 dx 2 primes. Dy prime equals to 6 over 5 dy 2 primes. So then this equation becomes dx 2 primes minus dy 2 primes plus 1 acting on e to minus y prime over square root of 5 u equals to 0. So this is the canonical form of equation for this variable, for this function. And now if we want to recover the variables for each, it is written, we should write these new variables in terms of the old ones. So dx 2 primes is square root of 6 over 5 d x plus 3 over 2 dy dy primes is also so it will be a square root of 3 over 2 probably. Yes, dy. So we have this transformation of differential operators, and now we need to find linear transformation of the variables themselves. So x 2 primes should be some combination of x and y. Or maybe we can express what is better to do. In principle, we can express old variables in terms of new ones. So we can say that x is equal to some ax 2 primes plus b y 2 primes. Y is c x to primes plus d y to primes. And if we now add, if we now act with these operators, so let us act with this operator on the first equation. Or maybe which? Ah, no, what the question? Where? So I multiplied by the so yeah, yes, I should have multiplied by yes, square root of 5/6. Right, thanks. And here probably was it fine or not? So here no, I did this computation wrong. So yes, it will be different. It will be 5/2 square root of 3. So now if we act with the first equation, it will give something like square root of 5/6 equals 2a. If I act with this equation here, it will give 0 equals 2b, because this y2 primes acts on the right side and gives b, and y acts on the left side and gives 0. So if we act, now act on the second equation, for example, again with the first one, it will give let's see, so square root of 5/6 3/2 equals to what we have in the right hand side. In the right hand side, this y2 primes acts on d, so it will be d. And finally act with this equation. So in the left hand side, no, sorry, no, sorry, I acted with this equation, and in the right hand side it gives c. And now for d, if you act with this operator here, it will be 5/2 square root of 3 equals to d. So basically, the point is that one matrix is a transformation in one direction, another matrix is transformation in the opposite direction. This these matrices are the same, because if we transform in the same direction, derivatives and coordinates, this matrices will be inverse. And we can also invert this matrix. So basically, it's how to get this transformation of coordinates. But mm, mm, you will need it only if you really meet some equation written in a non-canonical form, if it appears somehow. Usually people write everything already in the canonical form. So it's just to understand that the space that there is no, for example, there are no continuous parameters in these equations, so they can be brought to such canonical forms. Okay. So are there any other questions about what was going on the previous times? Okay, if no, maybe let us continue. Okay, so oh, by the way, I don't remember what is your name? Mm-hmm. But this is precisely what we studied maybe uh, the last week or when. It's in question. There is algebra of operators, which contains dx and x, and in principle some f of x, or we can consider also some functions of dx, for example, polynomials. It has some name, I don't remember precisely what is the name, but like this is called algebra of coordinate and momentum. Its coordinate is momentum, and the question is, what is the relation in this algebra? Namely, what is the commutator of dx and x? And the basic computation that should be done in this case is the following. This is some differential operator, and this is operator of multiplication by x. So to compute this, we need to take this commutator. So, but this notation is fine, right? So, you know such a notation, right? Or not? So, did you have it somewhere already or not? Hmm? Ah, oh, so it's, I thought that it could be somewhere at the mm, in the algebras or differential geometry. But in any case, there is such an operation which is called commutator, and it is AB minus BA. Um, And we can compute, so it is a remarkable property of it is that it can be used to define the so-called Lie algebras, namely the algebra that don't have multiplication but only such commutator. But anyway, let us compute the relations between these two. So to compute this, we need to act on some function f. So if something holds when acting on an arbitrary function, that it holds, then it holds for the operators. So and this computation is the following: we have dx times x f minus x dx acting on f. Mm. So when we act this way, we need to differentiate both x and f, and it will produce two terms. It will be x dx f plus f minus x dx f. So these two cancel, and we are left with f. So it says that commutator of dx and x is 1. So it's one computation. So is this clear or not? So we can consider this algebra and um, compute only not products but only such commutators. And this algebra will be closed under such operation. So, in particular, if we take a linear function, then we cannot get anything of higher degree. But so this was computation for just coordinate. But let us try to do the same for some function f. Let us see what happens if we compute such object e to a x dx e to minus ax. Let us act on some function f. And again, there will be the sum of two terms, e to ax minus a e to minus ax f plus plus the second term when this dx and x on f plus dx f. So it gives finally dx minus a acting on f, and the consequence is that if this yeah, so in the consequence is that if this holds for arbitrary f, then we can kind of remove this f and say that it holds as for the operators. So it has some interpretation in terms of Lie algebras and Lie groups, but you can treat it as just a convenient computational approach. So, like, is it clear or not? Does it explain anything? So, are there any questions, or we can? Huh? Just act with this operators on the left on the left uh, on these formulas. So, for example, for this first one, we have this equality, and we act with this equality on it. So, left hand side can act here. So we write in the square root of 5/6. Acting on so dx plus 3/2 dy x on x, so it equal to dx to primes acting on ax to primes plus by to primes. Right, so we just took this equality, which we want, and acted here. So because we can act with such operator on x, and we can act with such operator on a combination of x prime and y prime. Yeah. So the only thing to remember is that when you perform such transformations, you should change all possible variables at the same time. Because, for example, if it seemed that some variable was not changed, it does not mean that its derivative will not change, because when we write partial derivatives, we actually mean not just a derivative in x, but it is derivative in x with all other variables fixed. So it's derivative in x with fixed y. It is not indicated here, but it is understood by default. So partial derivative is not just partial derivative in some variable. It also depends on which other variables are fixed, and it is some point where it's easy to make some mistakes. So probably you've heard it or already met it somewhere. Okay, so are there any other questions? Okay, so let us go to the Fourier transform. So the last time we wrote a formula like this for the periodic function on a circle. We write an expansion like fn e to the 2 pi I n x for all integer n's. And what we checked, that if the function is continuous, then we can go in both directions. So this transformation from Fourier coefficients to functions given by this infinite sum, and the inverse transformation is fn equals to integral from 0 to 1 dx e to the minus 2 pi I and x f of x. So, and if a function is integrable in L1, then these fns are well defined. And we also studied, we also computed such integrals by parts, and studied that if a function is continuous, then so if function has discontinuities, then this offense behaves like 1 over n. If a function is continuous, then this maybe we can write in the correct notation. In C0 of S1, then this offense behave like 1 over n squared. So and so on. If it is in C1, then it will behave like 1 over n cubed, and so on. But let us study the following question. So there is this infinite sum, but how should we understand the sum? Can be understood, for example, as a limit of partial sums from minus k to k. And the question is how this limits, well, how these partial sums behave. So let us define f k as a sum from n equals to minus k to k fn e to the minus e to the 2 pi I nx. So we basically took these infinite tails and truncated them. So now, keeping in mind this property about behavior of these coefficients, we can check the following. So the first property, if we consider autonorm, well, if we consider the scalar product of f minus k, then it goes, so when k goes to infinity, it behaves like O of 1 over k. This is because what? Because these coefficients behave like 1 over n, and this left hand side is the, so it is also called norm. This norm of f minus fk. Sorry, I forgot to tell one important statement. Sorry. So there is this transformation, but now let us remember that we had a scalar product. It was defined by f times g in the integral of over dx f bar of x g of x. And now suppose that each of these functions is represented as the Fourier series. So fg will be the integral from 0 to 1 dx sum of fn bar e to the minus 2 pi I nx sum of g m e to the 2 pi I mx. So the question is, what is the value of this integral? Who can compute it? What should we do? Hmm? No. Mm-hmm. Fn bar because it was complex conjugate. Mm-hmm. Yes. Mm-hmm. Yes. And mm. In particular, uh, um, Fn in particular, mm, a square of a function equals to a sum of absolute value of n squared. So it means that this series for any function should be convergent. And we see it in this example that if f goes if f is discontinuous and this coefficient go like 1 over n, then partial sums uh, so the difference between function and its partial sum, the norm of this difference will be the sum from this from n greater than k absolute value of fn squared. And since this behaves like 1 over n, the sum itself will behave like 1 over k. And it goes to 0. So and this approximations by the partial sums converges to the original function in this O2 norm. In a sense, square of the difference goes to 0. And the square of the difference is, so on one side it is a sum of coefficients squared. On the other side it is the integral of absolute value of f squared. So. So. So there is such property, but let us ask what happens if we take some bad function. For example, if we take discontinuous function, what will be the behavior of this partial sums? And this is called Gibbs phenomenon. So namely, it's name. It's literally the question: what if f what if f is discontinuous? Uh, And if we want to study this phenomenon, it's actually enough to study one example of a discontinuous function because of the following argument. So suppose that we have this interval from 0 to 1, which is actually a circle. So 0 is identified with 1. And we have some function which is piecewise continuous, but has some discontinuities at this point. Well, let us draw it like this. And here it is, for example, continuous. And then we can present it as a sum of several functions that are discontinuous only at this point. So maybe no, how to say this. Let us introduce the model discontinuous function and choose it in the same way. It can be chosen as just the linear function from 0 to 1. This is x, this is f. So it is linear 1, and since 1 is identified with 0, it has discontinuity 1. So the just f of x is x. But here we have some function that is discontinuous at well, x mod 1, we can say. Because oh, because it is a function on a circle. But maybe it's actually easier to just draw some picture here, some pictures. So analogously to oh, maybe it's too much. Analogously to this function, we can draw such linear function that have the same discontinuities as this one at the same points. We just need some function that behaves like this. So it's linear, then it continues here, and then goes to this point. And another function here. So this is 1, 1, 0, 0. they're chosen in such a way that these points are the same. So this is, for example, x1, uh, well, x plus x minus, and here it's again x plus x minus, and here is some a, or maybe x is bad. No, this is x1, and this is some f plus f minus 1. So we construct linear function which has the same jump, and another linear function which has this jump in a different point. So this is x2, this is x2, and now if I subtract them, this original function will become continuous. So this is let us call it f1, and this is f2. So f minus f1 minus f2 is continuous. And since it's continuous, its coefficients will behave like 1 over n squared, and in such case, nothing interesting will happen. And all interesting phenomena will appear in this f1 and f2, which are essentially this f0 shifted in some direction, and also rescaled and shifted by 1. So essentially the same function. So to see everything, it's enough to consider just this. And, let us find its Fourier series. So take this definition. So oh, it's bad notation, f0, like just f. So fn equals to integral from 0 to 1 dx x e to the minus 2 pi I n x. So this integral can be integrated by parts. Actually, the original computation which we used to find the asymptotics of the coefficients. Dx x 1 over minus 2 pi I, sorry, d e to minus 2 pi I and x. And so then integrate by parts. And when we integrate by parts, this boundary terms give an integral contribution, because this x is discontinuous. It is 0 at 0 and 1 at 1. So we have I over 2 pi e to the minus 2 pi I n. That's for the boundary terms. Plus 1 over 2 pi I integral from 0 to 1 e to the minus 2 pi I n x dx. So this integral is equal to 1, because n is integer, and this integral I missed n here, sorry, pi n pi n. And this integral equals to 1 only if n equals to 0. But if n equals to 0, we just cannot do this. We need to compute the original integral. So f0 is the integral of x. It will be 1/2. So this is 0. And we write that fn's are I over 2 pi n e to the minus 2 pi I. So just I over 2 pi n for non-zero n, and f0 equals to 1/2. Okay. So, are there any questions about this computation? But let's now try to consider this partial sum. So this f case will equal to sum from minus k from n equals minus k to k. I over, so with n not equal to 0, so 0 should be excluded, e to the 2 pi I n x plus 1/2. So we can now take only 1/2 of this sum. So the sign is correct, probably, right? Yeah, so 1/2 of this sum is sum from n equals to 1 to k, minus sum of sine of 2 pi n x over pi n plus 1/2. So in general, this is not summable, but for us it will be interesting what happens for small x's, because in this case it's easy to analyze this sum. Well, in principle, it's also possible to study it for bigger x's, but let us restrict to this case. So when when x goes to 0, it is especially interesting for us because we know that these partial sums are all continuous. It's just sum of exponents. But the original function was discontinuous. And the first question is what is its value at 0, at discontinuity point? And then what is the behavior around this point? So of course, natural assumption is to say that it will be 1/2, in a sense, average value of left and right limit. But let us check this, because for example, it's clear that it is 1/2 when x equals to 0, because the sum just vanishes. So you can write it here. So k of 0 is 1/2. But the question is what happens around this. So, let us consider the situation when x is much less than 1. Maybe even kx is much less than 1. No, just let x much less than 1. It's enough. And then this partial sum will be 1/2 plus, and now let us obtain here the value. Let us gather here an x and write it like this. Sum from n equals to 1 to k, sine of 2 pi n x over pi n x times x. Idea of this is the following. We see that there is some function which depends on nx with x very, very small. And we compute a sum in n. So we can draw some picture about this. So let us call this function phi. This is some function phi of nx. So we have some from k equals to 1 to n, phi of nx times x, and x goes to 0. So the picture is this, and there is some phi, which is in our case this, and there are these points which are very, very close. This is nx, and this is phi of nx. So the distance between these neighboring points is precisely x. So the question is, what will be the limit of such expression if you, for example, keep nx on the upper limit fixed? So if the range for nx will be fixed. In a sense, let us say that this k is equal to some k tilde over x, an integer part. So who knows what will be the limit of this expression? No, what do you mean? There is some expression which depends on a variable nx, and this variable varies from 1 or basically from 0 to some k tilde. So does this remind you anything? Any construction from mathematical analysis? No, why zero? It's just a function. It's and not quickly oscillating. Hmm? No, like even if phi is 0, for example. No, it depends on the function. But, like, I'm actually trying to say that isn't it looking like that's the definition of a Riemann integral of some particular partial sum of the integral? So, hmm? So if you write some integral from from A to B of a function phi. Phi of x dx, it can be written as a limit when n goes to when delta x goes to 0, sum of phi of phi of nx n delta x times delta x, and n should be from, so that argument matches, so n should be from a over delta x to b over delta x. So
that expression is a real sum for
yes, yes. So it behaves like so if you send x really to 0, then the main part, the asymptotic. So this expression will be just the integral from 0 to well to k to k times x. To k times x of this phi of let us denote it y dy. Y is this variable nx. So if we go back to our formula and look at it, we can write that this partial sum fk of x is 1/2 minus the integral from 0 to kx sine y sine of 2 pi y over pi y dy. So asymptotically when x goes to 0. When so there is some name for this function, but we can just draw a plot of it. I forgot. Probably it's called integral sine, but we can just call it somehow. So if you draw just sine of x over x, it will be this. Sine of y over y. It will be something of this kind. And if I draw this function, it first grows quite fast because the value of sine of y over y is 1. So and then starts oscillating with a smaller and smaller amplitude. and it's an odd function. So uh, uh, let us call it Si of x. Maybe it's even correct name, but I just don't remember. Hmm? So integral sign, which is defined like integral from 0 to y to x sine. Well, let me maybe define it with the same constant that we had, 2 pi y over pi y dy. Uh, yes. So first it increases in the direction. In this direction it decreases, and the amplitude of these oscillations goes to 0. So it is something like this. And let me write here the correct constants: pi y over pi y. Well, so this partial sum is 1/2 minus this function. Si of kx. And so what happens when we send the k to infinity? We can always find a point which will go to 0, like 1 over k, but the value of this function will not change. So we can write that this f k of x over some, let us call it c over k. When k goes to infinity, k goes to infinity, it behaves like 1/2 minus this si integral sine of c. So in practice, it means what? That here is our sum. So picture will be the following. Here is our function. Let me maybe draw this function in the different fundamental domain. Let us say that it is let me choose um, so let us say that it is 0. No. So maybe it's better. So I don't know how to present it better, but let us just draw it as a periodic function. So this way. So if you look at this point, then we will have some function that goes to 0, and it will be precisely this function. So it will go like this, and go down, and so on. So so I should draw decreasing amplitude. Well, maybe it's too much, but vicinity of this point looks like this. So if you have discontinuity, then this partial sum has oscillations. So it's on one half, but in general, it is the same function, which is just squeezed. So, and it means that if you consider such expression like maximum over this integral, or maybe supremum, no, well, maximum just enough, a maximum of f of x minus f k of x x in 0 to 1 will be some constant. I don't remember precisely, but probably something like pi over 2 minus 1. It follows, it's a maximum of this integral sign, maybe up to some constant. And it does not go to 0, even if it's sum k to infinity. So in this case, these functions converge to the original function, but not uniformly.
This constant is the same for whatever function we choose, or it's a particular because we chose x?
It depends on discontinuity. So it's absolute value of discontinuity. I think that.
Only on that. I can choose any function, and if I fix this continuity, the constant is the same.
Yes. Because if you take difference of this function, if you take a discontinuous function and this model function, then the difference will converge uniformly, and the only contribution is from discontinuities. By the way, I didn't say it probably, but there is like, well, many things can be called theorems, but if f is continuous, then these partial sums converge uniformly. So if f is in, so if f is continuous, maximum of f x minus f k of x will behave will be of order 1 over k. So it goes to 0 when k goes to infinity. This is because we know we know a restriction on the coefficients of f. So this difference, f of x minus f k of x, is so absolute value of this difference is absolute value of a sum for n greater than absolute value of n greater than k, fn e to the 2 pi I n x. So it is less or equal than absolute value of, like, less or equal than sum of absolute values of this fn's, which behaves like maybe less or equal than sum of some constant over n squared. So it's a further 1 over k. So for continuous functions, we don't have anything like this. Everything just convert uniformly. So, are there any questions about this? So, this is normal situation. And by the way, it should also be clear why such behavior does not affect this L2 convergence. Because the norm of such a function goes to zero, since the range in which it oscillates also goes to zero. So, and then the range where it is essentially different from zero. So, these points behave typically like some a constant over k. So, are there any questions about this? Huh. Hmm? This one? Oh. So it is written that this partial sum equals to 1/2 minus the function, which is integral of sine of x over x. And plot of this sine of x over x is this. Here it is with sine minus, so I flipped it. And well, and there is some additional knowledge that this first oscillation of this function will be a little bit bigger than size than this difference. It can be just computed. We can see what is the value of this function on the first maximum. No, but actually, it is just some funny thing which can appear in practical application, and also maybe it is good to understand what this convergence, what this different convergences really mean. That something like this can happen, and but usually we will just avoid such situations. But are there any questions about this? So let us maybe so let us maybe switch to the next topic. to the Fourier transformation on a line. So here we had some formula for the integral. We had some formula which computed coefficients n for this function f, and this n's appeared as factors in the exponential. So we expanded everything in terms of periodic functions, and because of this, these n's were discrete. But now, if we have circle of infinite radius, this n will become a continuous parameter, and namely, if we work with functions on a line, we should define the Fourier transform of a function like f of p, f tilde of p is defined as the integral from minus infinity to plus infinity dx e to the minus I p x f of x. So it's of course a question when this integral is defined, but usually people think that even if it's not very well defined, we should find some way to compute it. For example, to regularize and then remove regularization, or to say that this contour is chosen in some appropriate way. So such things are quite flexible. And the question is, what is the inverse Fourier transform? So there is a statement that the inverse Fourier transform is given by almost the same formula, but with a different sign in the exponential, as it was here in principle, and with some factor in the measure. P over pi tilde of p. But this should be checked. So, namely, we should do this transformation twice. First, take function f, construct f tilde of p, its Fourier transform, and then try to reconstruct the original function. So. So suppose that we have this definition, and we want to compute inverse transformation, namely integral of minus infinity to plus infinity dp over pi So this is the definition of the Fourier transform, but uh, with a changed variable, so that it does not coincide with this x. So um, and here actually to compute this integral, we should do the same trick as before. To suppose that this original function decays at infinity, because of some properties of f. Basically, it is the same story. Then, if that it if f is continuous, then its Fourier image decays like 1 over p squared, right? Yes, like this. So we should assume that it decays at infinity, and then we can multiply it by e to the minus epsilon absolute value of p, and also write it here. So so again, we see that the only p dependence in this integral sits in these two exponents. And we can write that this is integral from minus infinity to plus infinity in dy, integral minus infinity to plus infinity dp over 2 pi e to minus epsilon absolute value of p plus I p x minus y y. So so let us postpone this computation and compute on the integral in p. So so it can be written as a sum of two integrals. Like this. I just wrote two parts of this integral in the same manner. And so now over 2 pi. So now the question to the audience: how to compute such integral? So what should be the answer? Mm-hmm. Mm-hmm. Yeah. So I'm writing it in such a way that it is easy to remember that integral from 0 to infinity dx e to minus lambda x equals to 1 over lambda. So the integral which I always keep in mind. It's Okay. So it's easy to remember. So there's always a question with all the signs, highs, and so on. But if you are sure that the real part of this expression is negative, and you can compare it to this integral for the case when it's when this is definitely positive and equals to 1/λ, and then modify it somehow. So the way to remember all the signs. So. Oh, you can say some intermediate answer. But no, but why do you need to group them? I wrote this precisely for this purpose, because look, if it is just integral of e to minus epsilon pi d dp, it will equal to 1/epsilon. But this is different only by modification of epsilon. So this first integral is e to minus epsilon, in this case minus ix plus iy, p dp, right? So it is not the same integral, but with some complex a complex number multiplying p here. So it is epsilon plus some imaginary part. So we just take the previous formula and write that it is 1 over epsilon minus ix plus iy. So because this integral, it's much easier to integrate exponential than trigonometric functions. So, because in principle, we see that if you take a real imaginary part, you will also get some result, but this way it's much easier, I think. And this integral is computed in the obvious way, because the integral of dx e to minus lambda x from a to b is equal to minus 1 over lambda e to minus lambda x from a to b. So we just need to substitute b equals infinity and a equals to 0. So the upper it vanishes on the upper limit, and it equals to 1 over lambda on the lower limit. And we can do the same with this integral. The only thing we need to know before computing this is that it is convergent, and the epsilon is added precisely for this purpose. So it converges at plus infinity. Otherwise, it would be just something oscillating. And I remind you that if f tilde of p was decaying at infinity, this modification does not break anything, because contribution from infinity was going to 0 anyway. So if you modify a function in this limit, it will not change the answer. Okay, so the answer is the following. It will be 1 over 2 pi overall, and one term will be 1 over epsilon plus I y minus x plus 1 over epsilon minus I y minus x. So there are different possible ways to write this. So we can write it by taking everything together. In this case, it will be epsilon over pi epsilon squared plus x minus y squared. And you can recognize here this delta sequence. So it is delta epsilon of x minus y, which has on this plot. So and if you want to compute this integral independently, you can also look at this expression directly and see that if we consider the function of x minus y, it has poles at I epsilon and at minus I epsilon. So two such poles, and when we integrate over the real line, we can change this integral either on one pole or on the other one. they have residues plus and minus 1. So this is delta sequence, and some that integral of this delta from 0 to infinity, from minus infinity to plus infinity. This delta epsilon of x minus y, delta epsilon of x dx is 1. And function itself goes to 0 in all points except 0. So we already saw this function in the for a transformation on a circle. So now if we substitute this here, then it will be integral from minus infinity to plus infinity dy. So no, is it clear or not? Or is everyone lost? Right. So what will be the answer here? What if we compute this? Yes. When epsilon goes to 0, it will be just f of x. Okay. So we found that this Fourier transform is actually inverse to this one. So now why do we do this? Because remember that we had the wave equation, right? So maybe let me erase this. So originally we studied the wave equation with 0 right hand side, but let us now add some function to the right hand side. So then u of t and x, we should be able to solve this equation with some trivial right hand side. And now let us see what happens if we substitute here this function u as a Fourier integral. So let us say that u of t and x is the integral over d omega over 2 pi. It's for the time variable dk over 2 pi e to minus I omega t plus I kx u tilde of omega and k. And let us do the same with the function f. Let us say that f of t and x is equal to the integral d omega over 2 pi and d k over 2 pi e to minus I omega t plus I k x f tilde of omega and k. So uh, the question to you, what happens when we differentiate this integral in t or in x? What should be modified in the right hand side?
Yeah, it depends on the regularity of u tilde.
Hmm?
But if u is sufficiently regular, you can differentiate the a to the e to the minus I omega t plus kx. And so when you do the first time with t, you get on one minus I omega. And when you do the second time, you get minus plus omega squared.
No, you take minus I twice. Minus I squared is minus 1.
Ah, okay.
So it will be minus omega squared plus k squared. So and multiplied by this Fourier image. So it acts by multiplication. So let us write the left hand side. It will be d omega over 2 pi and d k over 2 pi e to minus I omega t plus I kx. And so here will be minus omega squared plus k squared because of inverse sine f or u tilde of omega k. This will be the integral d omega over 2 pi and d k over 2 pi f tilde of omega k times e to minus I omega t plus I kx. So now we see that two Fourier transformations of two functions equal, so the functions themselves should also be equal. Therefore, u tilde of omega k equals to minus 1 over omega squared plus k squared, or minus k squared, f tilde of omega k. So here let us write this equality symbolically, because we need to understand what is the precise meaning of this, because in principle it is some quite bad object if you write it this way, because it is defined for real omega and k, but it has poles for omega equals to plus and minus k, and these poles are in the real plane. There are these two lines, and naively integral of such function will not be defined. It will be divergent. So we need to think about this. But the general idea is this, that when we want to solve some equation which does not which is linear and does not contain explicit dependence on coordinates, we can always solve it using the Fourier transform. Because after the Fourier transform, differential operators turn into the multiplication operators, and it is a kind of algebraic problem. We just take this Fourier image and divide by omega squared minus k squared. But So actually, we need to study it in more details because there is this problem, and there is actually it is the same problem that this problem itself is not uniquely defined. Because here, for example, I did not say anything about the initial conditions for you, and if it has some initial conditions, then the answer will depend on these initial conditions, and this answer formally depends only on f tilde. So it should be done more carefully, and the true answer should contain everything, initial condition on the right hand side. But there are situations where such approach does not create such problems. We can just say that, uh, that it is the answer. So, for example, it will be the case for the Laplace equation, where, to be precise, Poisson equation, where there is plus here. Okay, so are there any questions about this? Okay, so maybe that's all for today. Thanks for your attention.